Okay, let's begin. We actually have one more topic to cover for the test, and that's logarithms. So we'll jump into that. Now this one might be hit or miss. I can expect that many of you probably have not seen this, but how many of you have seen logarithms? Okay, so let's just go through it then. Start with the definition. So this is what a logarithm is. I just defined it basically in words. Notice that a logarithm is a power. Okay? So it's kind of another way to think of an exponential equation. You're just kind of thinking of it in terms of the power rather than the base being the star of the show. So the notation is you write log. The base is the little number that goes down here. There's a number that's here, but it might be an algebraic expression as well. And that is equal to the power that's over here. So that's sort of how you want to think of it. Okay? There's the base. That raised to that power gives you some number that you create. So there are certain rules that immediately fall out of this definition. In other words, the first rule is kind of like the definition of a logarithm. It says when you write log to the base a of b and you say that's equal to c, what that means is if I take the base a raised to the power c, I will get the number b. It's basically what that sentence is. Okay, so that's the first rule of a logarithm. So for example, you know that log to the base 2 of 8 would be what? 3. Right? I need to take 2 to the power 3 in order to get 8. That's basically how it is. There's another rule. Well, there are many rules. I'll tell you about mine. As logarithms turn powers into multiples. So for example, if I have log to the base a of something to a power, then I can take that power down and multiply the logarithm. That's because if you take something to a power and you raise it to another power, it's actually multiplication that happens in the power. So raising a power to another power gives you a multiplication. I'm not going to really go into the proof of anything, but that's sort of the idea. So that would mean something like I'm doing a random example. Log to the base 3 of x cubed is just equal to 3 log to the base 3 of x. You can always simplify a log by doing that. But just remember that the power has to be inside the logarithm itself. Okay? It's not the same as saying if I have log to the base 3 of x and the entire thing is raised to the power, it's not the same as log to the base 3 of x raised to the power. I want that should be 2. Now in this case, I can move the power down. In that case, I cannot. Because this one just means log times log times log. It doesn't mean that the thing inside is 2. I just want to emphasize. Rule 3. Logarithms can simplify products somehow. You guys know how? For those of you who know about it, what is log of x times y? Yeah?
It's log of ax plus log of ay.
Log to the base a of x plus log to the base a of y. Right? Logarithms can turn multiplication into addition. Right? One of the reasons why we like to think of things this way is because they simplify operations. Right? If you want to multiply two large numbers, it's much easier to add two large numbers. So, yeah, so if you see something like log to the base 7 of 5x squared, you could actually simplify that as log to the base 7 of 5 plus log to the base 7 x squared. And if you wanted to go further, you could even simplify this based on that rule. Log to the base 7 of 5 plus 2 log to the base 7 of x. So one reason why I'm telling you these rules is they'll allow you to simplify things, right? So you're given something that might be difficult to deal with, you can break it down into things that are easy to deal with. And so we realize that when we multiply things with the same base, we add the powers. Logs are powers, so that's why they turn multiplications into sums. I mean, the proof is a lot more stickier than that, but that's basically it. Let's go to rule 4. Log to the base a of x divided by 1. What do you think that becomes? Yeah? It's just a subtraction. You could actually use this rule. Just write this as x times y to the minus 1 separated, and then the minus 1 can come down in front. Or you could just remember that when you divide things with the same base, you subtract the powers. So this just becomes that minus that. So an example, log to the base 9. And when I write base a is representing any possible base. Usually your a will be greater than 1. Taking a log of a base less than 1 is usually pointless. So for example, if your base is a half to the x, right, you'll just realize that you can just write this as base 2. Right? You can always rewrite a number that's less than 1 to look as the inverse of something greater. So I should have mentioned that at the beginning, but things work out nicer when our bases are bigger than 1. But when I write a, I mean it represents any base greater than 1. So it can be base 2, base 3, base 7. It doesn't matter. These rules that I'm giving you, they'll work with any base. So I could say something like this x equals 1, x. I can actually break that down into log. So x plus 1 plus log. It's a 9. Rule 5. This one is called the change of base formula. You probably won't use often, but I'll use it to derive some rules later, so I'm going to tell you about it. You can change the base of a logarithm to be more convenient for you. So let's say if you have log to the base a of b, but somehow working in the base b is not very convenient, you can actually change the base with this formula. It's actually equal to log to the base c of b divided by log to the base c of a. So if for some reason the base c is more convenient to work with, and you're given something in base a, you can actually change the base with this formula. So let's give an example. If I ask you about log to the base 4 of 8. So some of you might recognize that, what that number is. Does anyone recognize it right away, what it is? Yeah? Huh? Right, because what you need to figure out when you look at this is what power do you have to raise 4 to in order to get 8, right? So you're like, okay, so 4 to the 1 is 4, so that's smaller, okay, but by the time you go 4 to the 2, you jump to 16. So you know it has to be a number between 1 and 2. Is it 1.5? It could be, but you're not sure. So it's not very convenient for you to work in base 4 because you're not used to thinking of 8 as base 4, right? So what you can do though is that you know both what 4 and 8 are in base 2. Base 2 would be a lot more convenient for you. So what you can do is you can apply this rule and you can say, oh, that's actually log to the base 2 of 8 divided by log to the base 2 of 4. And what's log to the base 2 of 8? 3, because I need to raise 2 to the power 3 in order to get 8. Log to the base 2 of 4. 2, because I need to raise base 2 to the power 2 in order to get 4. So it turns out that that answer is 3 over 2. It actually is right in the middle, 1.5. It didn't have to be, but it turns out it is. So that tells you that if you're handed, a situation is handed to you in a certain base, and it's not convenient to work in that base, you can switch the base if you want. And in calculus, that will often be what we want to do. And when we get to calculus, you'll see why we need to change the base. Because just as how in the case of exponentials, that there's a certain exponential function that's very convenient for calculus, e to the x, right? There is a certain log function that's very convenient for calculus, right? So sometimes if you're given a log in another base, you want to switch it to that base, the convenient base. You can use this base. First 5 rules, consider them important, memorize them. The next, I'm going to give you a few more rules, but they're kind of rules that you could derive relatively easy from the rules that I already told you, but I like to actually write them down because it's nice to actually memorize these rules as well, because when you can do that, it makes your life a lot easier in simplifying problems. There's just some things that it's nice to know right off the bat. So we're at rule 6. Log to the base a of 1. If I tell you the logarithm of 1, what is the answer? 0. It's always going to be 0. No matter what the base is, if you take the log of 1, it'll always 0. Why? Because a raised to the 0 gives you 1. Right? So technically you could use definition 1 to figure that out, but it's nice to, it's something that you can know right off the bat. It'll show up often enough to actually just know that. 7. I don't know if it's a rule really, or a warning. What's log of 0? It's undefined. And this is kind of, working in base 0 is not very convenient, but here, you know that our a is greater than 1. Why? Because let's say I gave you 2. What power can you raise 2 to in order to get 0? There's nothing you can raise 2 to get 0. Right? If you have a positive number, there is no power in existence that you can raise it to get a 0. So that's why log of 0 is undefined. You can also notice that log is, this can also talk about the domain of log if you think of it that way, which I'll mention afterwards, is you can't have the log of a negative number, because if I give you a positive number, you can't raise it to a power to turn it into a negative number. So a log is also undefined for when the thing you're logging is negative, right? Logs are only defined for positive things. Here's a nice rule that Again, it's obvious from rule 1, but it's nice to just know it right away. Let's say I take log to the base a of a to the x. What is that? What power do I have to raise a to in order to get a to the x? X. Right? Raise a to the x, you get a to the x. Right? That one kind of falls in your lap. But it's a very good rule to know. Right? So you would know something like, oh, log to the base 2 of 2 to the radical 3. Well, that's just radical 3. Once the base of the log, and if you're plugging in an exponential and it has the same base, you can think of the log and the exponential as kind of canceling each other. Right? You plug an exponential into log, they kill each other, and then you end up with the ends. Rule 9. Rule 9 says this rule works in the opposite way. This one isn't as obvious. It's not a difficult proof, but I won't show you the proof. You can figure it out in 2 or 3 steps if you'd want, but I'm not really going to do that. I did it in my other class, but I'm not going to do it here. The rule works in the opposite way. If I have a base a and I plug into its power log to the base a, those you can think of as kind of canceling as well, and that will give you x. So, example, if I have 3 raised to the power log to the base 3 of x squared, that is just x squared. Right? Whatever this thing inside the log is, that's what the entire expression will be. And again, I mean, calling some of these rules, they're kind of strong, but I guess I want you to think of it a certain way. So again, this rule, rule 10, is about notation. So remember I told you about e to the x being a very convenient exponential function to use. So it just so, it stands to reason that we kind of going to want to, when the base is e, we probably need to want to emphasize that somehow. And we do. So when you see log to the base e of something, which you'll never see that because I'll never actually write that, that we will denote as ln. So if you see this, what it means is the base is e. I'm just not going to write it. ln is called the natural logarithm. Because e is a very convenient base for us to work with, log to the base e ends up being a very convenient logarithm for us to work with. Okay? And so much so that we often denote it very differently. So we write ln. So whenever you see ln x, just realize that the base is e. I also want you to realize that even though it might look different from the logs that I've been writing before, it obeys all the same rules. I just want to emphasize that. It is a logarithm. We just write it differently. So it obeys all the log rules. So for example, if I have e to the ln of something, it's just a thing. If I have ln of e to the something, it's just a thing. What if I have ln of e? It's just 1, right? Because there's a power 1. If I have ln of x times y, I can still split that up by adding them together. That's all the rules will still work. Okay? Because it is a logarithm, we're just emphasizing that the base is special to us, so we have a different notation. Also, if you just have log of x and the base is not written, you can assume it's log to the base 10. But do be aware that ever in the future you branch off to a different discipline. These notations might actually change. If you read, for example, an advanced math textbook, you won't see ln in the textbook, right? They'll use this to represent ln, right? When you don't write a base, it's assuming that's the standard, right? Log to the base 10 tends to be the standard at lower level math because you always work in base 10, right? You have 10 figures that you're counting. But in math, in higher level math books, when they write log and no base, it's assumed to be base e, so don't get confused by that. If you go into really high level computer science, it'll assume to be base 2 because it's binary. So the standards might change based on the discipline that you're reading. But for our purposes, ln is base e, log with no base written is base 10, and all other cases I will specify the base I'm working with. I expect you to know if I write ln, the base is e, and if I don't write a base, it means base 10. So in other words, if you see log of 5 equals x, you could write that to mean 10 raised to the x equals 5. Why? Because there was an invisible 10 right there. Another approach. So rule 8 says that if you take a log of a base and you plug in the same base, they cancel each other and you get the x. And if you do it the opposite way, you take a log of a base and you plug in an exponential, it cancels the x. Anyone knows what that's about? Like what that means for two functions? It's not something we mentioned in the class, so you probably wouldn't remember. It tells that logs and exponentials, they share a very special relationship, are inverse functions. Because they reverse each other, right? One function does something and the other function undoes it, right? So that's what it means when you say log to the base a of a to the x equals x. Your exponential took something and did it to the x, but when you plug a log in there, it kills what you did before and gives you back the original, right? So one function does something and the other function undoes it. Right? And if that happens in both ways, you get what we call inverse functions. That's useful because that helps us to get to the graph really quick. To graph the log of an inverse, there's a special transformation that you do. You reflect in the line y equals x, right? Because your x's and y's are switching places. So for example, I know that the graph of an exponential looks like this. We did it last time. So this is y equals a to the x. If you want to figure out y equals ln of x, you put in the line here, y equals x, and you flip the mirror image over that line. You'll end up getting this graph. This would be y equals log to the base a of x. So notice that at 0 it's not defined, it never actually touches the y-axis. It's also never negative, which makes sense with what the definition that we used. So just like exponentials, the graphs are going to be very important for us to remember for logs, and the transformations. So the following. If I want to graph y equals log to the base a of x. And again, I'm assuming a is greater than 1. That's what the graph is going to do. If I want to graph log to the base a minus x, the graph is going to look like that. If I want to graph y equals minus log to the base a of x, then that's just the negative of this one. That means this flips upside down. If I want y equals log to the base minus log to the base a of minus x, then this graph flips upside down. So those are all your transformations in the logarithm. And of course you can stretch it, you can shift it up and down just like any other graph. But this is the basic graph. It passes through 1 on this axis because log of 1 is 0. That was basically your quick intro to logarithms. We'll be using them a lot. So let's actually do some examples. I want to make sure I'm catching this side of the board. Simplify the following. A. E to the 5 ln 2 to the log to the base 2 of 2 to the 5. Log to the base 2 of x minus log to the base 2 of x squared plus log base 2 of x to the 4th. I want you to combine these. E raised to the power ln of x squared minus 5 ln of y. Ln of the radical of x squared minus 1 over x times x plus 2 squared. This one I want you to expand. Solve these equations. Those examples will in the chapter. get through some of these. You have e to the 5 ln 2. How do you simplify that?
So the
Huh?
cancel the ln over e.
You can't do that. Why not? That's the important part. Why couldn't I do that? What did the rule say that when we can cancel ln of these? E to the ln of something is just the thing, right? What's the issue between this and that?
It's raised to the power. The power 5.
The 5. There's a 5 in front here that's not here. Notice that there could be a number here, I would have put it in the rule, but there isn't, right? So it's very important that those rules I wrote down, you guys remember. Because before you apply a rule, you have to make sure that the thing you're applying it to looks exactly like that. Right? So I can't cancel an ln and an e. In order to do that, they need to be literally right beside each other, right? E and in the power, the very first thing is you see is an ln. The 5 here messes that up. So what can I do? Yeah?
Move the 5, like raise the 2 to the 5th power.
Right. There's a rule I can apply in the power of the log that says a multiple of a log can move up to a power. So I can do that. That's true. Right? That's me using rule 2 or something. And now you can actually, those guys kind of kill each other and you end up with 2 to the 5, which is 32. So be careful of that. It's very important that you follow the rules exactly. Right? So if something doesn't fit in with the rule, you need to kind of tweak it a little bit before you apply a rule. There was another option here, and this is kind of using a law of exponents before. You can realize that this, when you're multiplying a power, it's the same as taking something to a power and raising that to another power. That's actually also the same thing, right? Because x to the a raised to the b is just x to the a times b. I can go backwards here, and inside the parentheses I can apply the rule, and again I end up with 2 to the 5th, which is that right here, and 32. So a couple ways you could have thought of it, but you need to make sure you're applying rules in the right order and you're applying them in the correct situations. So if it would be wrong to do something like cancel this and then take 5 times 2 and get 10. That would actually be the incorrect answer. So be careful how you're applying these rules. How does that one simplify? Yeah.
Cancel the 2 in the log to the 5th to the 5th.
Which one? This one
Yeah.
and that?
Yeah.
Alright, so here's the base. I have log to the same base. I can literally cancel that. You could also have canceled this one. You kind of have the option here and do that in power. But yeah, the 2 and log to the base 2 would cancel. And again, you would end up with 2 to the 5, which is equal to 32. Let's see. How would you combine these logs? Yes.
You multiply x and x4 and divided by x squared.
Yeah. So you remember that the subtraction is a division, so you can actually do log base 2 of x divided by x squared plus log to the base 2 of x to the 4th. And then you remember addition is multiplication, so that becomes log to the base 2 of x times x to the 4th over x squared. And you can actually simplify this. So that would become, when you combine that all into one log, that would become log to the base 2 of this x cubed. Or you could go a step further and write that as 3 log to the base 2 of x. Combining logs are going to be very convenient when you're trying to solve an equation. Expanding logs are going to be very convenient when you're actually doing calculus. So there are 2 different strategies going on. What about this one? Yeah?
You solve the logs in the power and then you just cancel it out.
Okay, how?
Will be ln x squared
E to the ln of x squared
divided by y to the power.
divided by y to the fifth. Right. So let's do that a couple steps here to see what happened. So e to this is ln of x squared minus, first took the 5 and brought it up here. It's ln of y to the fifth. And then there's a rule that says when two logs are subtracting, it means you're dividing the things. So then you end up with e to the ln of x to the squared over y to the fifth. And now you can do that. So that becomes x squared over y. So we'll stop there. I want you guys to actually try this on your own. So I won't consider this section finished, so the homework isn't due yet. But I will. There will be a quiz on up to this point. So try that and come back to you. But in terms of the topics that we needed to cover for the first test, this was it. This is going to be the last topic for the first test. You have your homeworks. Leave them here on the table, and I will see you guys on
The week on Tuesday.
Yeah.
I think this week is